So hello everyone, welcome back to our 7th lecture. And this lecture is a very special and very practical lecture, and it's called data preprocessing. All right. So data preprocessing is essentially the process of transforming data until you get it into a form until you get it into a usable form that you can do analysis with, that you can implement machine learning algorithms with. So that is going to be the focus of our class today. So far in our last 6 or so lectures, we focused on the actual algorithms. So we focused on neural networks, logistic regressions, and just actual machine learning algorithms. And here we'll actually focus on data preprocessing, which is going to be used to actually make every single one of those algorithms work. So with that being said, let's actually get started with our agenda for today. So first, we'll be discussing overfitting. Overfitting and underfitting, and we already talked a little bit about this in the last lecture when we talked about neural networks. So we talked overfitting, underfitting a little bit in the last lecture, but here we'll talk about this in a bit greater detail, and we'll also talk about some ways to actually combat this problem of overfitting and underfitting. Next, we'll focus on feature scaling. And again, we talked about feature scaling in the last programming exercise when we converted an image which was a grayscale pixel valued image from 0 to 255 to a value between 0 and 1. And we'll talk more about this in greater detail in this lecture as well. And next we'll talk about training, testing, and cross-validation. And then we'll talk about R squared. So R squared is essentially just a testing metric that we'll talk about. That we'll talk about in greater detail today. And lastly, we'll end with talking about one-hot encoding and something called imputation, which is essentially the process of of fixing missing data. And by the way, we did talk about the fixing missing data a little bit when we talked about our programming exercise with regression. But we'll again talk about imputation in greater detail in this lecture. So first, let's get started on overfitting and underfitting. 1 second. All right. Okay. So first, let's actually, in order to actually introduce overfitting and underfitting, let's just talk about some motivating example to actually introduce this concept. So let's say that you're given 9 data points, so 9 x y labeled points. Okay, let's say you're given 9 of these x comma y labeled points, and you want to find the best possible function actually modeling these 9 data points. So you have 9 sort of coordinate points, and you want to find the best possible function modeling it. So what would you then do? And if you will recall, this is a regression problem. So essentially, you're given some x values, and you want to predict a numerical output. Okay, and so this is a regression problem. So how exactly can you do this? So far in this course, we've only learned about one regression technique, that is linear regression. So that's essentially a regression technique when we assume that there's a linear relationship between our x or explanatory variables and our response variables or our y. Okay, so that's linear regression. But it turns out that in many complex phenomenon of linear regression just isn't very good or just isn't feasible at all, because of complex phenomena just can't be very well represented a lot of times by a linear model. So what do you then do? It turns out that you can create many more complex functions instead of a linear function. For example, you can create a polynomial function to actually go through all the data points instead of a linear function. And this, whenever you have a polynomial function go through the data, it's called polynomial regression. Okay. So we can fit our 9 data points using polynomial regression. And by the way, I guess linear regression is a subtask of polynomial regression when the degree is 1 in a sense. Okay. So you're given these 9 data points, and you want to use polynomial regression to actually model it. So then, what do? And it turns out that you can create an 8th-degree polynomial. Okay, so you can create an 8th-degree polynomial to go through every single one of these 9 data points perfectly with 100% accuracy every single time. Okay, so you have its 8-degree polynomial with 9 parameters, and you get 100% testing training accuracy. So then, aren't you good? I mean, I guess it's fine, right? Because if you have 100% training accuracy, wouldn't that mean that we are perfect in pretty much every scenario? But that's not true. Just because you have 100% training accuracy doesn't necessarily mean that you have 100% testing accuracy. And a lot of times when you have a really high training accuracy, you might have a very low testing accuracy. Okay, and that's what overfitting is. And this might seem abstract right now, so I guess in order to make it more concrete, let's look at the visualization. All right, so this is a very nice polynomial regression visualization. So essentially what this calculator sort of thing is, so this is a JavaScript program that, sorry, one second. So this is a JavaScript program, as you can see here. And essentially what this is that we can give our, we can give this model some number of XY coordinate pairs, okay? So 1, 3, so we can give it, in this case, we'll give it 9 XY coordinate pairs. And then it automatically finds us the equation of the line of a given degree, okay? So this essentially does polynomial regression for us, right? So, so what I did here is I have entered the data that I want to look at. So these are our 9 data points: 1, 3, 2, 7, 3, 6, 4, 18, so on and so forth. All right. So I guess this left column is the X column, and this column is the Y column. And we have 9 of these, and our goal is to find the best possible polynomial that actually models these 9 data points. So first, firstly, you see these are these 9 data points here. And first, let's actually fit a linear model to it. And we already learned about this when we talked about simple linear regression in the second lecture. So we have this this linear line, and this is the best fit line that models all these 9 data points. And this is an okay approximation, as you can see here. But let's see if you can do better than that. And if you increase your degree to 2, you see, yeah, this is a much better fit. And it turns out that when you just keep increasing your degree, 3, 4, 5, 6, 7, this gets better and better. You have a lower mean squared error for as you keep increasing your degree. And when you finally have a degree 8 polynomial, you see that this goes through every single one of these data points. And in general, if you have n number of data points, you can fit a n-1 degree polynomial to sort of go through every single one of these data points. And I guess the reasoning for this is just algebra. Okay, so I guess as an exercise, you can see why this is true. So now we have this 8-degree polynomial which goes through we have this 8-degree polynomial which goes through every single one of these data points perfectly without any error, right? However, you see that this still isn't very good, because and in order to actually show that, let's consider this one example. Let's say that we want to predict what our function outputs at x equals 1.3. So what's the y value at x equals 1.3? Okay. And just from looking at the table, you can reasonably guess that number is going to be somewhere between 3 and 7, maybe with a little bit of this variation. Maybe it's between 0 and 10. However, if you actually look at what x equals 1.3, if you look at what the function outputs at x equals 1.3, indeed you see that this is y equals almost 24, right? And this isn't a very good fit, right? You see that x equals 1.3 just doesn't work well. So looking at this model, you see that this works perfectly for the training set, but then it doesn't generalize well to testing sets. So when you have a new data point, you see that it just doesn't work very well at all. And because we only have 9 data points, even this polynomial might work okay for the test data. But as you keep increasing the degree of the polynomial, this 8th degree model, or this n-1 degree model, which goes through every single one of the data points, starts being worse and worse and worse, okay, for a testing set. So now let's actually go back to our discussion on overfitting. And let's actually talk about how what we just experienced fits with overfitting. how that's related to overfitting. So essentially, the way you could think of it is that the thing we just did. So the eighth degree polynomial is an example of an overfit model, and an overfit model is generally characterized by very high training accuracy, but low testing accuracy. Okay, so whenever this happens, and this is what happened out in our previous example when we had this eighth degree polynomial, we had high training accuracy but low testing accuracy, and that was indicative of an overfitting model. In general, overfitting occurs when the model fits very close to the training set. So in our case, it fit 100% to the training set. Although to be overfitting model, you don't have to have 100% training accuracy. So when it fits, and it fits the training set very well, but fails to generalize to some testing set. So essentially what happens is that the model memorizes sort of the data points instead of actually understanding the underlying structure of the data. Okay, and let me actually, this might seem pretty confusing, sort of how can a model memorize data points? But I guess to make this more concrete, let me present an analogy, okay? So let's say that you're studying for some math test. Let's say you're studying for an addition test, for example, all right? So let's compare how two students studied. So one student could just look at 100 addition problems and just memorize the answers to memorize the questions and the answers. So if that person went to the test, he would only do good if the exact same problems came up. So he would do perfectly if the exact same problems came up. However, he didn't really understand the underlying structure of the data. He didn't really understand underlying structure of addition. So he couldn't really, he wouldn't be able to do well if he had questions that he hadn't seen before. So that's sort of a real life analogy to overfitting. Okay. So another way of saying this is that the model fits to the noise in the data instead of the underlying structure. Okay, that's another way of sort of saying this overfitting. And now let's actually introduce the opposite of overfitting, that is underfitting. Okay, let's talk about underfitting. And underfitting, as I said before, is the exact opposite of overfitting, and it occurs usually when the model is too simple. So an overfit model usually occurs when the model is way too complex, but an underfit model usually occurs when it's too simple. And the definition of underfitting is when the model does not capture the underlying structure of the data. But now we're going to be wondering what's different between overfitting and underfitting, other than just the complexity of the model. And I guess the best way to think of it is that overfitting is essentially when the model, I guess, gives an illusion that it's working well. It worked very well for the training set. Okay, but here an underfit model doesn't even give an illusion that it's working well. It just simply doesn't capture the underlying structure of the data, and does low training accuracy and low testing accuracy is representative of an underfitting model. All right. So now we've introduced what overfitting is and what underfitting is. But there's no use of learning what it is if you can't sort of combat this. So now let's learn how to actually combat overfitting and underfitting. Okay, so how to combat overfitting and underfitting. And one technique that we'll introduce in this lecture is called regularization. So regularization is a technique that's actually used to combat overfitting and underfitting. And essentially what regularization does is that it combats overfitting by helping the model create a less complex model. So it sort of makes the model less complex and thus less prone to overfitting. Okay, so now let's actually describe how regularization works. So this is what I'm going to do to actually explain regularization. So first I'll talk about what is regularization, and then I'll sort of explain why it works and how you can use regularization to actually combat this problem of overfitting and underfitting. So essentially what regularization is that you add, okay, so before I actually explain what it is, let's go debrief on cost functions. So if you recall from our previous lectures, cost functions are essentially functions that measure how badly or how well the model is doing, okay? And this, for example, if we add 1 over n here, this right over here is the cost function for linear regression, all right? This is the cost function for linear regression. As we saw there, the many machine learning models just with this traditional cost function are very prone to overfitting. So to combat this problem, we add this term right over here. This is called a regularization term. And adding this regularization term here helps majorly with overfitting. And here's why. So usually it turns out that when you have very large parameter values, that usually corresponds to an overfit model. Thus, if you keep your parameter values small, then you would be less prone to overfitting, right? And essentially what this lambda term does here is that it adds a bunch of theta 0, theta 1 up until theta n to your cost function. So it adds a bunch of the theta 0, theta 1 and all those parameters. And because we have added these parameters, we know that it's an advantage to actually have small values of theta 0, have small parameter values, because that would lead to a smaller cost function, right? So that's sort of like an intuition to why regularization works well. And now you may be wondering what this lambda thing is here. So lambda is essentially a parameter that you can adjust to actually control your regularization. So if you suspect that your model is overfitting, just increase your value of lambda, okay, and vice versa. So, and I guess in order to see that, you see that if you have let's say lambda equals 50, for example. If you have lambda equals 50, then you have your regular cost function plus 50 times theta 1 squared plus theta 2 squared all the way until theta n squared. So the greater the value of lambda is, the more the model is penalized for large values of large parameter values, and thus it's to your advantage to keep the parameter values small. So that's what regularization is. So to recap, regularization technique to combat overfitting, and the way you perform regularization is, if you suspect your model is overfitting, increase the value of lambda, and then increase this lambda value, and then your model might perform better. Okay, but regularization isn't the only technique to combat overfitting and underfitting. Indeed, there exist many more techniques to actually do so. I've grouped all of them into one. It's sort of a one table here, just because, in my opinion, these things are quite a bit more intuitive than regularization. So number one. So first thing is increasing the number of epochs. So what is an epoch? So one way to actually combat underfitting is to do this. Okay, but what is an epoch? So let's actually define this term here. You might not know what it is. So epoch is essentially training a data set one time. So one epoch is training a data set one time. Okay. So epoch just refers to training, and we talked a little bit about this and I guess we sort of introduced this in the last lecture, but we never really defined it at all. So if you increase the number of epochs, then usually your model underfits less. Okay. So one solution to underfitting is doing this. Conversely, to combat overfitting, you might want to decrease the number of epochs. Okay. And in order to actually see this in action, I recommend you watch our previous video when I actually implemented a neural network model wherein we classify handwritten digits. In that example, we saw that when we had so in there we had 5 epochs, which isn't very much, but we saw that when we had 5 epochs right over here, when we had 5 epochs, we had a lower accuracy than when we had 4 epochs. And one reason for this might be that the model might be overfitting because we had too many epochs. Okay, so that's why you can see that decreasing the number of epochs, this just helps with overfitting. Another thing is increasing the number of features. So this helps with underfitting. So one reason for this might be that a lot of times you just don't give enough input or enough features or enough input features to actually create a complex enough model to actually represent a phenomenon. Okay, sometimes there's a phenomenon, you just give it too little features to actually represent the phenomenon, and thus increasing the number of features just makes your model underfit less. Okay, and conversely, you want to decrease the number of features when you do overfitting. And well, not lastly, but one other thing I would like to do is get more training examples. So getting more training examples a lot of times helps in both underfitting and overfitting. Okay, but just getting more training examples isn't the solution to all of your machine learning problems. So all too often, a lot of people just want to get more training examples to just want to get more training examples because they think it will always work. But a lot of times, some of these other techniques work better. Although getting more training examples is still a very promising alternative. And one last thing that I haven't mentioned here, that I haven't written here, is just the complexity of the model. A lot of the time, in order to actually combat an underfitting model, you would want to increase the complexity of the model. So, for example, if you're performing some classification task, and currently you are using logistic regression, you might want to use a neural network instead to actually have the model work better. And conversely, use a less complex model when you're overfitting. And so that's it for overfitting and underfitting. So now let's move on to R squared. Yeah, so what is R squared? So R squared is a testing metric that we want to use. It's essentially a testing metric to see how well the model is doing. So far we have discussed two testing metrics in particular. So we talked about accuracy and F1 scores. So let's just talk about both of these. So we really haven't talked about accuracy in very high amount of detail yet, but that's just because accuracy is quite intuitive. Accuracy in a classification task is just the number of test examples that our model represented correctly divided by the total number of test examples. Okay, so that's what accuracy is. And we also talked about F1 scores. And while we didn't have a whole lecture on F1 scores, we talked about F1 scores, I believe, in a little amount of detail when Dr. Willard talked about his logistic regression lecture. Thirdly, now let's talk about R squared. So R squared is a testing metric. So it's written like this. So R squared is a testing metric for regression. So R squared is a testing metric for regression, and it essentially represents the amount of variation in the phenomenon, okay, in a certain phenomenon accounted for by the regression model. Okay, so every data set has some sort of variation in it, and a typical goal of a regression model is to capture as much of that variation as possible, and that's why R squared is such a popular metric for regression. And now let's think about how R squared is computed or calculated. So essentially the traditional way to calculate R squared is by first calculating how much of the variation was not accounted for by the regression model and subtracting it from 1. Okay, so let's actually think about how we can actually represent how much variation wasn't accounted for by the model. So S is residual. So that's essentially just the total residual is the total residual value of the model, and it's essentially the metric we use to actually represent this. So let's actually talk about what S's residual is. So let's say you have a bunch of data points here, and you have this regression line passing through this data point, and S's residual is essentially the cost function. So this is the mean square error cost function. This squared plus this squared plus this squared plus this squared, this squared, this squared, on and on. Okay, so that's what S's residual is. Okay, so it's the sum of yi minus y hat sub I, so your actual minus predicted square. Okay, and your actual total value is yi minus this y bar right over here. So in order to actually represent total error, essentially the way we do it is by comparing your regression model with, I guess, the worst possible regression model. So this worst possible regression model is y bar, and it's essentially the average of all the y values in our data. Okay, so this is a constant. This y bar is a constant value. So if we graph it, we might get something like this. Okay, And then essentially, so we might get something like this. And then the mean square error between each of the data points and this y bar line is called a y bar line squared. So this mean square error between y bar and our data points is called the total residual. Okay, so that's essentially how we compute R squared. And don't worry if you didn't understand all the details here. That's you don't really have to understand all of it to actually be able to implement it. Just know that it's a testing metric that's popularly used in regression. And Strawman will actually be implementing R squared in Python. So that's it for my part of the lecture for today. Now I'll pass it on to Strawman, who'll discuss data preprocessing and feature scaling, and things of that nature. So Strawman, would you like to get started?
Yeah, thank you, Shreyas, for the great presentation. Could you stop sharing your screen?
Yep.
Yep.
Can you now share it?
Yeah.
All right. Okay. Nice.
So, as Shreyas said earlier, data preprocessing is the method to transform data into a better understandable format for the machine learning algorithm. And we need to do this because the data is often incomplete, inconsistent, and is likely to contain many errors. And to fix that, we usually always do data preprocessing. So a really common thing to do in data preprocessing is feature scaling. Feature scaling is the method used to normalize the range of independent variables, or basically the features of the data. So let's take this data set into example. As you can see here, we have age and salary, but the age and salary have completely different scales. What the machine learning algorithm might do is take the salary into more importance because it has a higher scale, but we don't want that. So to fix that, we have to do feature scaling. So there are two main methods for feature scaling: normalization and standardization. And we're going to talk about both of them in the next slides. So normalization is the method that scales the features from values of 0 to 1. So it does that by this formula. So the normalized x is equal to the x minus the minimum of that feature minus the maximum of the feature minus the minimum of the feature. So let's take this data set into example. So when you normalize each value here, you get this data set. And let's just take this data point as an example so you can understand. So, wait, can you all see my screen? Can everyone see my screen?
Yep, I can see it, yeah.
Okay, so let's take this data point into example. So so we do 44 minus the minimum of this feature, which is 27. So 44 minus 27 divided by 50 minus 27, because 50 is the maximum, and you get 0.739. So that's kind of how normalization works. Now let's move on to standardization. So standardization scales the value of the features based on the standard normal distribution. So the standard normal distribution is a special type of distribution curve that has a mean of 0 and a standard deviation of 1. And that's why it's centered at 0 and has iterations of 1. And in standardization, we're trying to kind of do the same thing to the features, trying to fit the features to a normal distribution curve based on the mean and the standard deviation. And we do this using this formula. So what this formula is stating that the normal standardized x value is going to be equal to the actual x value minus the mean divided by the standard deviation. So let's again take this data set into example, and when we standardize it, we get these values. And so if you take this data point as an example, you can see that the x value here is 44, and the mean of these features are 42.5, and the standard deviation is about 14.8. So when you do that calculation, you get 0.1007383. And that's how you do standardization. And now let's talk about imputation. So imputation is basically the process to replace the null values. So basically replace the missing data. So what can you do with the missing data? So there are many things you can do. You can actually drop the missing data, but sometimes, most of the times, you don't want to do this because some key information might get lost. So you can replace the missing data. So you can replace it by the mean or the median, or even sometimes the mode. But the important thing to keep in mind when you're actually replacing the data is that you don't want to change the data set too much. Now let's talk about categorical transformations. So categorical transformations is the process of which the categorical variables are converted into a form that could be read into the machine learning algorithm. So for example, some categorical variables might be yes, no, and the machine learning algorithm can't really understand the yes, no. So we have to change them to a numerical form so that the machine learning algorithm could understand it. And actually, some machine learning algorithms can actually understand categorical variables, but it's still really important to know how to do categorical transformations. And there are two main methods to do categorical transformations: one-hot encoding and label or integer encoding. So let's start talking about one-hot encoding. So in one-hot encoding, the variable is removed and a new binary input is added for each unique variable value in a different column. And this is going to be clear to you from this example. So in this data set, we have 3 unique colors: red, yellow, and green. And so each of the unique variables are in these columns, and as you can see here, the first color is red, so there's a 1 in red, and the rest is 0, and vice versa, and on and on. So now let's talk about integer or label encoding. So in integer encoding, each unique categorical variable is assigned to integer value. This is actually kind of self-explanatory. So let's look at this, the y values here. And we can see there's 3 unique categorical variables, and each of the variables are assigned 0, 1, and 2. So when it's encoded, so each variable is assigned to the corresponding y value. So here caliber 0, and that's 0, and that's u is 2, and that's 2. So now let's actually look at how we can perform data preprocessing through Python. So let me just share my screen to right here. And today we're going to be working with insurance data, and I'm going to go get more into that. But first, we need to import all of our essential libraries. So I'm going to start off by importing pandas and NumPy. So import pandas as PD. Can everyone see my screen okay?
Yep, I can see. Yeah, I can see it. Yeah.
Pandas is PD and NumPy is NP. As NP. Now we can start with the reading of the CSV file. So df equals pd.read CSV insurance.csv. Now let's just print the 5 variables. And so today we're going to be predicting the insurance that a person has to pay based on where they live in the United States, if they smoke or not, the amount of children they have, their BMI, their gender, and their age. And so as you can see here, we have some categorical variables. And first, let's do our categorical transformations. For the gender and smoker, we're going to do integer encoding to change up the values, the numerical ones. And for the region, we're going to do one-hot encoding. So let's start. So I'm going to start off by doing I'm going to do the integer encoding using label encoder. So let's start off sklearn.preprocessing from. And we're going to import label encoder. Okay, so now that we've done that, we have to, oops, I spelled sklearn.preprocessing wrong. Sorry. Okay, so now that we've done that, we can assign label encoder into a variable. So label encoder is equal to label encoder. And now let's start by transforming the gender. So is equal to a label encoder dot fit transform let's see what I did wrong here. Oh, my bad. Okay, now we can do the same thing for the smoker column. So smoker. Okay, now let's visualize what happened. So as you can see, so the female's 0 and the male's 1 for the gender, and if they smoke, the yes is 1 and the no is 0. And now that we've done all the label encoding, let's do the one-hot encoding, and we're gonna do that using pandas. And so now we have to create a dummies data frame that actually has all the encoded values of the region. So pd dot get dummies. Now df dot region. Okay, now let's just look at this data frame. Okay, as you can see here, we have all the encoded values. So all we need to do is merge both of the data frames. So df equals pd dot concat df and dummies, and the axis will be equal to columns. And this so I spelled columns wrong. Oh, actually, I didn't spell it wrong. I just forgot. Okay, this might be a little tedious, but I'm only doing this so you can understand it a little better. And now let's look at what we've done. So df.head. So as you can see, we have all the encoded values merged with the original data frame. And now all we need to do is drop the region and drop one of these, so that we can so that we don't fall into the dummy variable trap. So df equals df dot drop columns equals region and southwest. So region and southwest. And let's do df.head to see if it worked. Yep, it worked. Now we can start with the train test split. So first, for that, we have to import train test split from sklearn.model selection. So now import train test split. Okay. Now I have to assign my x and my y variables, and the x variables is going to be the x variables are going to be everything but the charges column, and the y variable is only going to be the charges column. So first, for the x, I'll do df dot drop columns, and the columns are going to be equal to charges. And now for the y variable, we will do just df charges. Okay, so now that we have that, we can start with the train test split. So x train comma x test comma y train comma y test is equal to train test split. We will now do train test split on x comma y, and then we're gonna pick our random state as 20, and then we're gonna do an 80-20 split. So our test size will be 0.2. Test size will be 0.2. Okay, so now that we have that, we can start on the normalization and standardization. So I'm gonna make two different models, one for all the normalized data and one for all the standardized data, and then we can see how their R2 scores compare. So let's start off with the normalizing. So from sklearn dot preprocessing import standard scalar. So I'm doing standardization first. Standard scalar. Okay, and now I can just say x, okay, standard scalar is equal to standard scalar. So standard scalar is equal to standard scalar. And now we can do x train normalized. So now I'm assigning different variables for the x train. I'm doing x train standardized, x and x test standardized, and I'm gonna transform them both using the x train and x test data. So x train standardized is equal to standard scalar dot fit transform. We'll transform the x train. Now we'll do the same thing for x test. Okay. So now that we've done the standardization, I'll start on the normalization. So from sklearn.preprocessing, I'll import min-max scalar. Min-max scalar. Okay, now I will I'll just copy paste this. Actually, I'll just do scalar is equal to scalar is equal to min-max scalar. Okay, now I'll just copy paste both of these for the simplicity. So just gotta change that to normalized. So normalized and change that to scalar. And I'll just, run it. And now I'll do the same thing for the testing data. So x test normalized is equal to scalar dot fit transform x test. Okay, so now that we have that done, we can start creating the model. So from sklearn, we will import linear model, and we can say model is equal to linear model dot linear regression. Linear regression. And now now we can start fitting the data. So we'll start off with the standardized data. So model dot fit. We can start with this x train standardized and y train. Okay, so now that we have that done, we can start with start predicting the x test standardized. So model dot, so y hat is equal to model dot predict. We'll predict all the x test standardized. Okay, so now that we've done that, we can start with the R2 score. So for the R2 score, we can do import from sklearn.metrics, from sklearn.metrics, we can import R2 score. Okay, so now that we've done that, we can start with the prediction. So R2 score of y test and y hat. So y test and y hat. So as we can, we have a 0.79 R2 score for our for our standardized data. Now let's look at our what the R2 score is going to be for our normalized data. So model normalized is equal to a linear model dot linear regression. Okay, so now that we have that, we can just do model normalized dot fit transform x train normalized and y train. So x train normalized. Okay, so now we can start with the prediction of the test x test normalized. So y hat normalized is equal to model.predict x test normalized. So normalized. So predict that. Okay, and now we just have to run the R2 score for the y hat normalized. Did I not change? Let's see what I did wrong here. No, y test and y hat normalized. So a model normalized equals linear model dot linear regression, then model normalized dot fit x train normalized and y train. Y hat normalized is equal to x test normalized. Oh, I predicted from the model of the standardized data. So that's why I did so bad. So if I did model normalized, I ran these again, and now it's 0.7953. So the R2 score for the standardized data is 0.958, and the R2 score for the normalized data is 0.7958 and 0.7953. So there's a little difference, but not that much. And we are done with the programming part. Do you guys have any questions? Let's see the chat. Any questions? Feel free to unmute and ask. Shreyas, I guess we're done.
Yeah, so if you guys don't have any questions today, that's fine. If you get any questions while you're reviewing the materials or doing the assignments, please you can please ask it in Google. Oh,
all right. So can you go to the slide before the categorical transformation? I missed it. Okay, sure.
okay, let's go back.
Categorical transformation. Imputation. So imputations, all imputation is the process to replace a missing data. So when you have some NaN value, you can either drop the data or you can replace the data. But this is single imputation. So in single imputation, you can either drop the data or just replace the missing data. And let's see. What is the difference between regularization and normalization? Shreyas, do you want to take this?
Yeah, sure. So if you go back to 1 second, let me actually share my screen here.
Right, stop sharing it. Yeah.
All right. All right. So essentially the difference is the following. So regularization is essentially just a technique used to count 1 second, guys. So I'm not sure why it just doesn't work here, but let's go back to this slide. Okay. So regularization is essentially the process that's just used to combat overfitting. So regularization is just adding this term, and we use that to sort of combat overfitting. But normalization, on the other hand, is let me go back to So normalization is essentially just so normalization is a completely different technique. So it's essentially used to it's essentially used to convert data from a big range to some smaller range. Okay, so to some standard range, pretty much. So
it just scales the values.
Yeah. So essentially, the reason we do normalization is so our models don't I guess advantage one feature over the other just because of its size. So that's how those two things are different. So regularization is just used to combat overfitting, and normalization is used to have all our data points in the same range. So is that good? Is that sufficient for you?
Do you guys have any more questions?
I'll also say that it's important when you think about regularization and normalization together, that if you were to perform regularization on data that had very different scales, like age and income, you'd be penalizing the model for having one parameter, let's say for age, that's much bigger than the parameter for income, just because age is a smaller value. And normalization helps to move all those variables onto the same scale so that regularization can kind of penalize large parameters equally amongst all of the variables.
Yep. Thank you, Dr. Roller. That was a great explanation.
Any more questions?
Yeah, I can't really see the chat.
And I just want to say one more thing, that it might not be clear why imputation is important. It might seem easiest in general that if you don't have the right number of data points for a single observation, to just skip that observation or leave it out of training. But that could be a problem if you're in business or trying to make any prediction whatsoever. If all of the data that you need to make predictions for don't have all the data points. So throwing things out is not always a good option.
And also in real life, most real life data sets do have missing values in them. So missing values are actually very pervasive in that sense too.
And then I guess one final note, when you're looking at your data initially, it's important to try to check for outliers. So if you were to, for example, find a typo in one of the ages in the data set we were looking at, and instead of a person being 44 years old, somebody had entered it incorrectly and it said 444 years old. Well, first of all, that's probably not physically possible. But second of all, it's going to throw off your model because it's going to learn a different relationship based on that really high value that falls outside the normal range. So you really have to be careful. There's a saying in math and computer science, it's called garbage in, garbage out. And it means if you put garbage into a model, you're not going to get good stuff out of it. So you have to be careful that the data you're plugging in is valid, clean data. And that's why, although this isn't the most exciting topic, it's probably not as cool as neural networks. It's one of the most important, because if you don't pre-process your data correctly, it doesn't matter what model you use, you're going to get bad answers out. And so I'd really recommend that everybody focus a lot on the homework for this lecture and go back and review the slides later, because this is something that's really important to building a strong data science or machine learning project.
Well, currently we aren't really planning on having like a workshop kind of meeting, but if you guys really want to, we might be able to just we might be able to put that into the schedule somehow.
Yeah.
Let's maybe we can add a poll to the homework or just in the classroom to see if people would attend if we held something like that.
Yeah, that's a great idea. Yeah, we'll do that.
That's a good idea.
And then the next lecture on Thursday, we'll be talking about applications of machine learning. So as part of that lecture, we'll discuss a few different projects and that Shravan and Shreyas have worked on, and something that I've worked on. And so maybe those will help give you some ideas for projects for the final project as well. But if nothing else, thank you, gentlemen, for a wonderful lecture. And everyone have a great night.
All right, yeah. Thank you, Shravan and Dr. Willard, and see you later.